Welcome to Rational Science. Today we're going to be doing a little bit of a recap, little synthesis of what we covered the last 2 weeks on special relativity, specifically time and mass. And then we're going to be moving on to length contraction, distance traveled contraction, whatever they contracted. Okay, so let's start with time first. This is what we covered a couple weeks ago. And just so we review some of the issues related to time and special relativity. And specifically, the issue is that there is no definition of time. And because of that, we have all kinds of problems in our understanding. Or not really our understanding, the explanations special relativists give for anything related to time. No definition, you have no explanation or physical interpretation, right? No mechanism. And here's the first one, okay? Summary of time. Father Universe does not recognize motion. Father Universe does not recognize time. What do we mean by that? We mean that Father Universe only recognizes location, existence, what exists out there, okay? Father Universe is every atom in the universe at a given distance from all others, okay? So all that every atom has, any atom has, is location. And if it has location, it's an object, in this case an atom, right? It exists. It exists pursuant to the definition of exist, which is objects that have location. Father Universe only exists in the present mode. He recognizes no motion or time. He recognizes only what we could call present now, related to time, right? Present now, a point in time. Eternity. Now is eternity, right? Location is eternity. Instant, moment, location. That's what it is. That's all that Father Universe is. Every atom at a given location with respect to all others. And one of the issues is simultaneity, which is one of the issues that special relativity brings up. In fact, it's probably the most important one related to time. And that's that the notion out there is that things don't happen at the same time, according to the observers. In other words, opinions. And that's a notion we have to tear down. We have to destroy that completely. No such monster in physics. In physics, all we have is existence. Every atom in the universe is at a given location. Whatever happens, right, happens within a single frame of the universal movie. Now, we use the word happens, but happens takes up at least 2 frames. But an atom can only be in one frame at a time, one location at a time. Can't be in 2 locations, 2 frames of the movie at the same time. So the issue is when there's some kind of action, we have to look at where the atoms were in a given frame. Not in the reference frame. Do not confuse that with mathematical reference frame. We're talking about the frame of the universal movie. Okay? And so we have here a way of looking at this, right? Here we have God taking a picture of Father Universe. And Father Universe is just every atom in the universe at a given distance from all others. Father Universe occupies, as you can see there at the bottom, only a single frame in the universal movie. What is that frame? That frame, you can say, is simultaneity. In other words, 2 atoms are there in that frame, and they're a given distance from each other. And then in the next frame of the universal movie, they both move to a different location and so on down the line. So we say simultaneity because that's a word related to time. We say that takes up several frames. But when something happened, like if there was an explosion and there were 2 explosions somewhere in the universe, and they happened within the single frame of the universal movie, in other words, the starting of the phenomenon happened there in a single frame, right? Then we do have simultaneity. It's what is inside a single frame. That is the definition of simultaneous, instant, moment, point in time, the present, the now, the timelessness, and eternity. They all mean the same thing. It's a single frame, location and existence. That's all that we have in a single frame. Okay, and we have here the universal movie, the simultaneity. Okay, let me show that here. You have an event happen. We have two supernovas there in frame number 632. Okay, and so the question is, the first atoms that started popping or whatever, right? They had a given location, a given distance from everything else in the universe in frame 632. That's when the supernova started. Okay, so there is no if, ands, or buts. It all happened within that single frame. It could only have happened within that single frame. Now what happens? The thing takes up several frames, this explosion, and the first observer there that you see closer to the two supernovas, he's closer to the one on the top, the supernova that's on the upper left, and so he's going to receive the light from that supernova before he receives the light from the second supernova, which is a little farther away. So you can see that in frame 634, he's receiving the supernova flash in his eyes, but he hasn't received the supernova flash from the second supernova. Okay, and meanwhile, the second observer, who is much farther away, he doesn't receive any of the light yet. Okay, because it hasn't covered the distance. Okay, so what happens in frame 635? Well, finally, the first observer receives the flash from the second supernova. He's already seen the first one, and it turns out that the observer, number two, he hasn't seen any of it yet. He starts seeing it for the first time in frame 636. But when did the supernova happen? Well, that simultaneously happened in frame 632. No one can change that. Not even God, not even Father Universe. It just happened in that frame of the movie. Okay, and so that's what you need to understand about simultaneity, about a point in time, about now, about the present. There is no such notion as time. See, they mix up all these notions. They mix up time, which takes up at least two frames or more, right? And they mix that up with what happens in a single frame, which is the notion of simultaneity or moment or, time, cross-section of time, point in time that they're going to analyze. And there's a contradiction there because an atom can only be in one frame. It can't be in two frames, okay? Unless you're in mathematical physics, where they say you branch off into different universes and you make a clone of yourself in every step you take. That's not the case in science, okay? Now, here you have frame 632. That's when the event happened, okay? That's when the two supernovas were starting to happen. That's where the atoms were in that frame of the film, okay? So you can't change that. That's fixed. Atoms can only be at one place at a time. Okay, and one thing you have to remember, Father Universe, because Father Universe is just every atom in the universe at a given location. It's a static notion. Father Universe does not remember the past. He has senility, you could say, amnesia. He goes to sleep in a given frame of the movie, right? And he doesn't wake up for a trillion years. When he wakes up, all the atoms now have moved to the next location. Then he goes to sleep for another trillion years and so on down the line. So here you have him. He doesn't have a computer. He doesn't have a filing cabinet. He has no idea what happened in the past. Okay, Father Universe does not have memory. Okay, and that's one of the things that is required for time. You need absolute memory, to have memory. Same for motion. If you're going to look at motion, you have to remember where the object was, in a previous frame. And we record all that in our brains. And so we say, okay, we take motion for granted, right? And then we take time for granted. And it's not so. Every atom of your body only occupies one location per frame of the movie, okay? And when it's no longer, when it's at a new frame, it's no longer at the previous frame. And that's very hard for people to understand sometimes, okay? Okay, so here we have the way they see it in relativity. They think that you're creating new U's in every single frame. They think that the previous frame still is there, right? The previous location, your previous atoms, in the previous frame so that you can travel back in time, as they say, right, and meet yourself sometime in the past. No, that's Hollywood nonsense. That's got nothing to do with science or with physics. The way it works is the way you see that dot at the top, the ball at the top. It occupies many locations, but as you can see, there's no memory of what that of the different locations that ball had. The one on the bottom, on the other hand, you can see all the locations there. And special relativity looks at it like the way you see it at the bottom. All the balls leaving different balls in different locations so that you can go to one of those locations and stand on one of those balls. That's the way they see it. And you can see that in the film at the bottom. In frame 631, you see only you. That's you there. But in frame 632, you moved an inch or a meter or a foot or whatever, and there's two U's now. There's this previous U that was there, and it's in the same frame of the film as you are in now. And the same with frame number 3. Now you have 3 of U's, and so on down the line. So by the time you get to frame 636, not to mention gazillions of frames, right, in your life, every split second, right, you're leaving someone behind that's you. And so special relativity says that you can go to the past or to the future and see one of you in a frame because you're still here and so is that person at the same time because you're both in the same frame of the movie. And so, special relativity's notion of time has to do with math and not with physics. It has nothing to do with reality, with what is. It's just mathematical gibberish. That's all it is. And because of that, they talk about faster than light. And what's faster than light? Well, they need it for 2 reasons. One, to be able to go to the past, right, or to the future, and also to visit a, black hole or a wormhole or whatever. But the other one is so that they give you hope that we can get out of the solar system someday. If we can go faster than light, not only can we reach Mars in very short time, but imagine going to the nearest star, Alpha Centauri, the Centauri system out there, 4.3 light years away. That's traveling at the speed of light one way, you reach 4.3 years, right? And coming back, round trip, rounding off, you just talk about 9 years. And that's too long. Nobody can imagine that happening. People traveling for 9 years, back and forth. For what? Will anybody fund such an operation? Or project? So what they do is they say, but we can beat the speed of light. And for that, they needed faster than light, right? So they created all these mechanisms. And the big problem about that is that it's in the literature. That's the big problem. I mean, if they want to talk about that in Hollywood, no biggie. You can invent anything in Hollywood, make, special effects and say, hey, this person travels faster than light, or, take the Enterprise and just beam me up or down, Scotty, right? No problem. That's magic. And magic is okay where it belongs, but not in physics, not in science. And these people are bringing all this magic into science to beat the speed of light, which they all acknowledge after studying 10 years at the university, right? They all acknowledge that nothing can beat the speed of light according to special relativity. And then they want to overrule it. They want to skirt it. They want to circumvent this limit. They don't like that limit. So here it is. This is essentially it. Summary of faster than light. Faster than light is for Hollywood special effects. It's nonsense. It's good for, science fiction, fantasy. That's great. But it's unscientific. Don't bring it into science. Don't bring it into physics. Don't bring it into the scientific literature, which is what these people do. Okay? FDL should not have been there in the first place. Who approved this? Who were the peer reviewers who approved faster than light? When they all know, they all study, they all memorize, they all read the catechism of special relativity in general, right? That says that nothing can travel faster than light. They don't know why, and that's maybe why they try to skirt it, but they all have to, put their hand in the Bible and say, hey, I swear to God that, light doesn't travel faster than 300,000 kilometers per second, little c. And so we have a problem because on the one hand, they all swear to God that it can't travel faster than light. Nothing can travel faster than light, but then they immediately write papers that get published where they circumvent the speed of light or show mechanisms and whatever. You know why? Because they want to be able to travel outside the solar system. If they can't, then we're all dead here. This is our tomb here on Earth, right? No tachyons, wormholes, or warp drivel, as I call it. They call it warp drive. I call it warp drivel. That's what it is. It's all drivel, all this stuff. How does any of this stuff make it to the literature? That's what you got to ask yourself. I mean, if they want to talk about it at the bar, you know, at the water cooler over there in Harvard or Cambridge or whatever, go ahead. But don't bring it into science. How is this stuff approved for publication? That's what you got to ask yourself. And it's done with your money. Okay? Very important. All these people are funded, you know, to study this stuff, to create equations for this nonsense, none of which exists. None of which has anything to do with reality. So are we paying these guys to just develop, you know, equations for inexistent stuff? You know, unicorns and leprechauns? Is that what they're developing equations for? It's only to use to give hope for escaping the solar system, right, our planet. And then in order to do that, they have to create negative mass, negative energy, negative time. They create all these negatives. Yeah, if you weigh minus 20 pounds, whatever that means, right, I guess you can travel faster than light. You'll probably be floating up in the air, right? I mean, it's nonsense. Absolute nonsense. What is negative mass? What is negative energy? How does this stuff make it to the so-called scientific literature? And yeah, these irrational ideas only have the purpose of circumventing special relativity's maximum speed limit. They don't like the fact that light has a speed limit and that they cannot outrun it. They absolutely detest that. They want to have something to do also with their equation. They say, well, what if we put a negative sign? What would happen then? Yeah, I mean, you can put a negative house. What does negative house mean? You know, it means that you don't have a house, or you have it only in your dreams. I mean, what does that mean? And under the rope model, we can see why the speed of light is not only a constant, but why it's so fast. We can show both of those graphically. You don't need to go to college. You probably don't even need to go to high school. A 5-year-old kid can probably understand it. So here it is, okay? That's what it is, the electromagnetic wave that Maxwell and all these people in the 19th century came up with. We're replacing it with a rope, a pair of twined threads. A thread is not a field is not a thread, so we're not just making words here. Field is what you see there. Bunch of vectors, numbers. What's a field? Values at each point in space. So both field and vectors, of which fields are made, right? They're all numbers. That's all they are. And yeah, because this came out of mathematics. So when you look at a wave, and especially when you see it flying by you, very scary stuff. But when you see a wave, you're looking at a mathematical concept. You're not looking at a thing. You cannot say that light is a wave or is mediated by a wave, because a wave is what you see there, a bunch of numbers. That's all a wave is. We're replacing that with a physical object. We're saying light is mediated by a pair of twined threads that look pretty much like DNA. Okay, that's what it is. Okay, and so the speed of light is fast because you have a torsion instead of an up and down transverse wave. That's the first issue. Torsion, prove it to yourself, fastest wave known to man. In fact, it's the fastest thing that you can imagine. There's nothing faster than a wave, than torsion on a rope light, two-strand rope. Superman, the Flash, none of them can beat a torsion, because the torsion is already connected at the other end. You know, the rope is connected, or the mediator is already connected at the other end, whatever it is, right? It looks something like this, okay? Okay, so you can see that, you know, you don't have to travel over there. It's already over there. As soon as you turn this, you know, the other end is already moving. Okay, so that's why, you know, light is so fast, because it's a torsion wave, not a transverse wave. Transverse wave, in fact, is the slowest wave known to man. It's slower than a longitudinal wave. Longitudinal wave just has to go back and forth, whereas the transverse wave has to go up and then come back down. So, you know, when they have these seismic events, they measure, which generate both longitudinal and transverse waves. The longitudinal waves travel 1.7 times faster than the transverse waves. So we know that longitudinal waves are faster than transverse waves, which they say is what light is, right? So light should be slower than sound, I guess. You hear the thunder before you see the lightning, that kind of thing. So something is wrong with the transverse wave. You can't use that. And that has to do with speed. Now, why is it a constant? Well, you can see there, little c has been measured billions of times, okay, confirmed that it's a constant. Travels 300,000 kilometers per second, rounding off, right? And it's equal to an inverse relation between frequency and wavelength. That lambda, that's wavelength, right? And so you have the little f and lambda, right? And when one goes up, the other one goes down, and vice versa, to keep the little c constant. That doesn't happen with all waves, okay? Keep that in mind. You have sound waves, all these others. They can go, not sound waves specifically, but other waves can go faster than, in other words, there's no inverse relation necessarily between frequency and wavelength. You can raise both the frequency and the wavelength, and that wave will go higher. But little c is different than just velocity of a wave. Little c is a special type of speed, and it's known as a constant, known as 300,000 kilometers per second. So little c is a constant. And as frequency goes up, wavelength goes down, and vice versa. And you can see why. There you have 16 on the bottom, 16 links, okay, making up that rope. And if you untorque it, you see the inverse relation. Now you have fewer links, and each link is longer. So the wavelength has increased, link length, and there are fewer links, and vice versa. Okay, and that's why not only does it explain the speed of light, but also why light is a constant. The only entity that can simulate the speed of light, mediator for light, is a rope-like mechanism. Two-strand rope will probably do. Okay, so that's what we're proposing. Here we have the construction. Looks more or less like that for not only the light, but an atom. So you have an atom, and what you have is one thread goes around and builds this ball of yarn that encapsulates the other thread from every rope in the universe that converges upon our atom. And one thread goes through the center of the atom, the other one just goes around and encapsulates it. And that's what our atom looks like. So there's no attachment between the rope and the atom as if they were two separate entities. No, one turns into the other, and then on the other side it continues, going to another atom, the rope. Okay, so that's the construction quickly there. So you can see what we're proposing. Here's the basic system that we're proposing. We're saying there's two atoms there, and they're connected by a rope. Okay, very thin, unimaginably thin threads. Okay. So here they're very, very big, but this is the best way we can illustrate it. But you have to think of this as the atom being the size of the Earth, and the threads that make up the rope are the size of your sewing needle, okay, compared to the Earth. More or less like that. That would be a better relation for what we're talking about. But anyways, we have these pair of twined threads. They unite any two atoms in the universe. So that's our basic system. You can imagine this as being connected to tons of other pairs, right? In other words, a rope extends from each one of these atoms to other atoms and so on down the line. And so that's the basic system. You see the 2D version, the 3D version. The atom expands and contracts, and when it does so, doing its quantum jump, it torques the rope. Why? Because the rope is part of the atom. It's an extension of the atom, you could say, right? It's not a separate entity. It just flows from it. Okay, so that's our proposal, and one last one so that people see why you don't add the speed of the train to the speed of the light coming out of the train. In other words, you have your car, you turn your headlights on, and the speed of light will be always 300,000 be measured to be 300,000 kilometers per second, no matter how fast you travel, or even if you're standing still. And here's why: because every atom, as you move, eats into the rope, which makes up the atom. Okay, so all you're doing is sliding like a bead on an abacus. Okay, you're not pushing on the rope. In other words, the rope is going through you. Okay, so you're eating into the rope that makes the atom, and multiply that times gazillion atoms in the universe, and you get an idea, how this system that we're proposing works. Very easy stuff, really. It's kindergarten stuff. Once you see pictures, it's easier to understand than to go into math and trying to figure out, what does that equation really represent? The math is good. It's good. It's good to have that math in the background because it gives you a description, right, of how things move, how they behave. But math cannot tell you what is. And that's the problem with all of mathematical physics. You won't find a single entity, a single object in all of mathematical physics. That's the problem. What you have is descriptions of motion, quantitative description of motion. You never find a single object. Field is not an object. Energy is not an object. Mass is not an object. Time is not an object. But they treat them as such. They bend time. They move the mass. They vibrate the field. They transfer the energy. They think it's a ball or something. Okay, so that does it for time, more or less. I think you can go back to the previous videos and see some more of it if you're interested in understanding a little more. But here we're just summarizing what we covered previous weeks. Okay, let's move on to mass. What about mass? Mass in special relativity. Well, what is that? Well, the big problem, again, always the big problem in all of mathematical physics, specifically you could say in special relativity, is that there are no definitions. There are no definitions. And so they get away with murder because they say, well, time, we don't really know what time is. Energy, well, we don't know what energy is. They don't know what anything is. They don't know what mass is. They have like 7 different definitions according to the Wikipedia. So they have all these words. They don't have a definition for any of them. And with those words, they're going to use them to make their case. And so they're talking about X's and Y's. What's X? Oh, I don't know. What's Y? I don't know. But let me tell you, the X moves this way and the Y went that way. And what are they talking about? So this is where the problem is. The problem is these people have not defined the words with which they make their cases. They all remain undefined. And there's a reason for that as well. And the reason is that, they can't define them because they're concepts. And they're going to be using them as objects, as things. They're going to move them around. They're going to bend time. They're going to bend time. They're going to transfer the energy. They're going to vibrate the field. And so if they define it as a thing, fine, they can do that. But these are not things. These are numbers. And so they have to use them as numbers. And then they say, well, but I can't use them as physical objects. So they cheat and they cross the line, bringing all their words into physics. That's where the problem is. Okay. And so here, mass, where the problem is, summary of mass. Mass is a question of definitions. Okay, what is mass? Well, Newton essentially defined it as quantity of matter. And we all understand that. I mean, we can picture it. We can we can get an idea of what he's talking about when he says quantity of matter. We don't have a unit of matter. But we can say, okay, there's so much matter. Let's assume, like we do in the rope model, that the atom, the hydrogen atom, is the unit of mass. Okay, so all you have to do is count the number of hydrogen atoms, and you count a big atom like uranium, 92 protons, 92 atoms, 92 hydrogen atoms, plus 200 plus. 218, I think it is, neutrons. So you count every one of those as a hydrogen atom. And all you do is just add it up. It's 140 some neutrons, and the total comes up to 200 plus 218, I think, units, which would be 218 hydrogen atoms. So you would consider this a big atom. That's all it is, a bunch of hydrogen atoms. That's all the uranium atom is. And so if you look at it that way, you can say, okay, what's the unit of mass? the hydrogen atom. How many units of mass does this object have? 1 trillion. And then you have the number, you have the quantity of matter. What do we do with quantity of matter? We count them. We count every atom in there and say this object has exactly 1 trillion atoms. That's the mass of that atom, of that object. Okay, it's got 1 trillion hydrogen atoms. That's the quantity of matter version. Okay, what they had to do, since they measure everything instead of counting, because they can't count atoms, right? So they said, okay, we're going to measure. And so they started measuring. And that's where they got confused, because then they mixed mass with weight. Okay, and they say, well, how do you measure mass? Well, we weigh it and we put it on a scale and measure. How much does that thing weigh? Well, again, we put it on the scale and measure it. So we talk about kilograms for both, for mass and for weight. Kilograms should be used really only for weight and not for mass. Mass should be counting. You should count atoms. You should give me a number in terms of atoms. That's the way it should work. And that's not what we do. We measure by weighing. That's how we determine mass. Okay, so what's the problem? The problem is that they invented this thing called rest mass. And they use the word rest mass. People say, oh, what could they be talking about? Well, I'll tell you what they're talking about. They're talking about quantity of matter, because when the thing is at rest, it's not moving, so we don't have any motion, we don't have any momentum, we don't have any, acceleration, any velocity. It's standing still. What are we talking about? Quantity of matter. So rest mass is quantity of matter. Why don't they call it quantity of matter? Because it's better to say rest mass, because they're going to contrast it with the next one, relativistic mass. What is relativistic mass? Weight. That's what it is. Because now they're talking about the force the thing, whatever you're measuring there, the force it applies, the pressure applies on a scale. That's what they're doing. Okay. And the funny thing about that is that, yeah, you can only do that because when they talk about relativistic mass, they're going to introduce the speed of light. They're saying, well, the mass changes as the closer you get to the speed of light. And what do we mean by that? Well, we mean you're pressing down on a scale. But see, you can only travel at the speed of light, not here on Earth. It's got to be out there in the cosmos. So the scenario is always a cosmic scenario where you see a rocket or a ball or whatever you want to see, a ruler, right? And it moves at close to the speed of light. And then they say, well, it weighs more, it's thinner, it shrunk. And you get into these time evaluations. What are we talking about? Well, we're talking about how it approaches an object, a celestial object, and that's known as gravity. And the funny thing about that is that special relativity is a gravity-less theory. There is no gravity in special relativity. Why? Because it's flatland. It's you can't fall down in flatland. There's no gravity in flatland. And that's the issue with this relativistic mass. They're doing it in a context of gravity. So they have a contradiction, a fundamental contradiction. Because the only way an object can speed at the speed of light towards, for example, a star or a planet is in the cosmic scenario. It's got to be out there. It can't be here on Earth. There's no special relativity here on Earth. The special relativity is out there in space. And so if the object is falling towards the sun, that's gravity. And special relativity says we don't do gravity. It's a gravity-less scenario. So you try to explain that. They have a fundamental contradiction. Okay, so what's the issue? The issue is that if the number of atoms, right, goes up, then you have more atoms. In other words, if this thing, because of speed or because of whatever, increases its mass, then what we're saying is it acquired more atoms. That's what we're saying. Okay, there's no such thing as pressure in this case. We're not talking about pressure. We're saying we have more atoms. The thing has become more, acquired more atoms. Okay, that's the notion of quantity of matter. But if you're talking about speed, then you're talking about weight. You're talking on how much it presses down upon the scale. And on the cosmic scenario, the only way you can visualize that is it approaching a star or a planet. gravity. Okay? So proper mass doesn't change. In other words, if the special relativistic notion is that if the thing is traveling with you, it doesn't change its mass. It only changes for the observer who is measuring you from far away. For them, they measure something different. Who cares? What's that got to do with science? What's that got to do with physics? So he measures something different. Well, he's wrong, because whatever he measures, whether more or less, it doesn't really affect the object itself. The object, obviously, in its proper frame of reference, has a certain weight, certain mass, right? Actually, weight, because that's how we measure mass. We weigh it. And so it's got a certain weight locally. And that's those are the number of atoms that thing has. You have a ball, a bowling ball maybe. It's got all these atoms in there. And whatever atoms it's got, it doesn't change. And if it's in the local frame, it weighs whatever it weighs, 2 pounds, 3 pounds, whatever. From far away, you can say, well, it weighs more because you're traveling at the speed of light. Well, it weighs for you, but the ball only has so much matter in it. So they have a problem because they're talking about weight, but they call it mass. And that's when they get confused. Language is a problem. And again, weight just means bigger pressure on the scale. That's all it means. So, and that's what they're talking about. They're not talking about relativistic mass. They're talking about weight. Why they invented this term special relativistic mass, I have no idea. They could have stayed with weight and we were done. Okay, so here we have a scenario. We have this rocket, okay, and it's flying through the from one star to another, and it gets bigger because mass increases, right? And here you see it, okay. So it's getting bigger because it's approaching the other star. Is that true? It's going on the speed of light, right? Or almost the speed of light, this rocket. And what they're saying, no, the rocket does not get bigger. What happens is the observer there, he's measuring a greater mass. But he's saying that the object in its local frame has not changed its mass. So what are they talking about? I mean, either it changed its mass or it didn't. And they're saying it didn't, but the guy measures it as if it did. And so what does that have to do with physics, with reality, with what's actually out there? Okay? The number of atoms has not increased in a single frame of that universal movie. Whether the observer measured something different, well, that's his problem. He's got to go to a psychiatrist. His readings are off. He's got to measure the exact number of atoms that thing had, no matter where, in any frame of the universal movie. Okay? So here we have two elephants, okay? And they're going to fall towards different suns. One falls to a small star, the other one falls to a big star, right? Well, the guy on the right is going to fall faster, okay? Because there's greater gravity in the one on the guy on the right. Okay, and so this is the issue that at a given distance from the surfaces of these two stars, okay, they both have the same rest mass, which is 5 tons, which is the number of atoms comprising each elephant. It's exactly the same. Okay, and in any frame of the film in which they fall, those elephants do not shrink. They don't get bigger. They don't get fatter. They don't get slimmer. They always have the same number of atoms. Speed has nothing to do with the number of atoms they're made of, and that's what rest mass is. But as they fall, what changes is what? Weight. That's what changes. And so this is where the problem is. They call that relativistic mass when they should simply call it weight, because they're just falling towards, a star. And we call that weight, right? You fall towards the earth. Why? Because of gravity. What is that? That's called weight. Okay, so I'm sorry to tell you, that there is no such thing as relativistic mass. It's just weight. And here we see what happens in each frame of the film. Okay, what you have is the elephants start out, they both have 5 tons no matter what in each frame of the film. By 5 tons, I mean that the number of atoms has not changed. What has changed is the weight, right? As the elephants that occupy different locations with respect to their stars, they're going to have different weights. So the 5 tons, meaning the rest mass, always remains the same. What changes is the weight all the way down. And so, try to tell that to a special relativist. He will not understand because he does everything with calculations. He doesn't have a visualization of what's happening there. He cannot make sense of it, right? He just makes sense of the math, but not of the physics of it. That's where the problem is. Okay, so here's why the elephants have a different weight. Okay, this is the rope model explanation, right? You can see that every atom of that elephant, here we only picked one atom in one of its toes, right? And you can see that those atoms are tied to every atom of the star that is attracting them. Okay, so you can see why they have different weights. They have different weights because the number of ropes converging upon that toe, that atom in the toe, right? One atom, right, is greater on the guy on the right than on the guy on the left. That's the only difference between this, okay? And yes, every atom in the universe is bound to every other atom in the universe. Bound, by bound, I mean it converts into an atom, which then converts again into a rope and so on down the line ad infinitum. Okay, so you can see why their weights are different, okay? But the number of atoms in each elephant continues to be measured like 5 tons, meaning they're the same amount of atoms. Okay, they have the same number of atoms in both cases. Okay, so here we have 2 atoms so that you can see, because every atom has to be treated separately. Okay, here we have it. You have 2 atoms now. Okay, and you can see that if you do that with every atom in the elephant's body, you're going to have a big mess there of ropes. Okay, but every atom in the elephant is bound to every atom in the sun, in each one of those stars. And some people say, well, do the ropes go through each other? That's the one everybody asks. And they never ask the question they should be asking. See, and the question is, do neutrinos go through matter? Do fields go through fields? Do energies go through energies? Do masses go through mass? Is there a single space-time or many space-time? Are there many fields or just one field? And see, they treat them as concepts when they need to treat them as concepts, and they treat them as objects when they treat them as objects. And then they talk about superposition of particles in quantum mechanics. Nobody asks, well, does that mean that if there's a particle coming across and meets another particle and they superimpose and then they continue flowing, does that mean one went through the other? Yes, that's exactly what it means, but nobody asks the question. Everybody asks about the rope. How do the ropes go through each other? And the answer is all theories. There's not a single theory ever imagined by man where objects do not go through objects. Okay? And so if you have a theory that you believe, oh, my theory doesn't have that, I'm going to show you it does. So you better check your theories, because all theories implicitly have objects going through objects, electricity going through electricity, fields going through fields, waves going through waves. It's impossible not to do that. Okay? And so whatever you have as objects, as things, as mediators for light, gravity, etc., magnetism, whatever you propose, it's going right through something else. You can't avoid it. Okay? So think about that. So don't ask about the rope. Yeah, ropes go through ropes. They're always tight. Rope is always taut, right? It's always pulled taut. And ropes go through ropes, just like that. And you say, how can that possibly be? Yeah, that's the thing that kept everyone from understanding how our universe works all these thousands of years. Because nobody imagined that if an atom is bound to an atom, or like Professor Muller says from Berkeley, every atom in your body is being pulled by every atom on Earth, and every atom of your body is pulling on every atom of Earth. How do you pull if you don't have an elongated mediator between any 2 atoms of your body and every atom of the Earth? So yes, the issue is that no one ever pondered the possibility that in this invisible region There are atoms connected to atoms through these elongated things that connect these atoms, that bind them or interconnect them, right? And nobody ever figured out that, yes, you can go right through with your hand, right through all these mediators. And nobody even pondered that. They say, no, there's nothing here. Yeah, there is something there. You just can't see it or touch it. Just like you can't see the air, you can't see the ropes, in this case, what we propose, that binds all atoms. Okay, so here we have another version of our elephants, okay? You can see what's happening there. As one elephant is falling towards its son, you can see what's happening to the ropes. They're fanning out, and so the acceleration increases. And that's the acceleration of gravity there in a nutshell, in a picture. Okay? So it's easy to understand, no problem. You just have to go to, you see your shrink, right? About ropes going through ropes and things going through things. That's the only one that keeps everybody from understanding. From not understanding, I guess they understand it, but they don't. And they say, how can it go through rope? I cannot explain. That's magic. No, we have magic all around us. Quantum proposes magic. Relativity proposes magic. String theory proposes magic. They're all magic. They all go through each other. There's no such thing as not going through another object. Okay? And so you have to come to terms, and if you can't live with that, go see your shrink tomorrow morning. Okay, so here's God taking a picture of weight. Okay, weight has to be a static concept, right? What is that, 5 tons? Well, it's the number of atoms at a given location. At a given location. What is location? A static concept. Okay, we take a snapshot. We should be able to take a snapshot of weight. What is weight? Number of atoms from, in this case, one star connected to one atom in the elephant. That's called weight. That's the weight of that atom at that distance from that star. Okay. Single frame in the universal movie. Okay. It's not a force. It's a tension. Okay. Newton put force there. No, there's no force. Why is there no force? Because it's not distance traveled. It's separation. Fixed separation. Distance of physics between, in this case, the elephant, or one atom in the elephant, and the surface of the star to which it's falling. Okay. What is weight? Number of effective ropes. The closer you get, the ropes fan out, you have more effective ropes. Okay. And the rest mass of the elephants have not changed, or of the star for that matter. Okay. It's just the quantity of atoms. So I think it's straightforward. The problem with special relativity is that they never define the word mass. They never will. They can't. They shouldn't, because if they do, their theory goes out the window. So they can't define it. They can't define field. They can't define energy. They won't, and they should not, because unless they want to destroy their theory. And so they use it as a concept, a mathematical concept over here, and then they use it as a physical object when they give you the physical interpretation. And that's where the falsehood occurs, okay? That's when they lie, or they fool themselves, whichever. Okay, let's move on to distance. What's the problem with distance? Guess what? Definitions. Again, the problem with mathematical physics is definition. Big definitions. Why? Because in the religion of mathematical physics, they define words for math, quantities, right? Numbers. And they have all these words necessary to deal in their world, in the world of math. But then they want to bring these words into physics because they have, or science, right? Because they have no other way of explaining, what their math tells them. And so they bring these words without scrutiny, they just bring them directly into the real world of physics, of explanations, of physical interpretations, of mechanisms and causes. They bring them over and they want to use them for those purposes. So they say, look, what we have here is a field. What do you mean a field? What is a field? I thought it was a bunch of numbers. And now they're going to vibrate the field over here. And they have time. right? Okay, so what is time? Well, we don't know what it is. We count seconds, minutes, years, months, whatever, decades. And they bring that into physics, into the real world, into the world of explanations, in what people want to understand, right? And they say, the field vibrates, time bends, and mass moves. And energy is another word. They've never defined energy. They don't know what energy is because energy is not a what. Energy is a number, bunch of numbers maybe, right? Followed by a unit, right? Maybe it's ergs, right? Or joules or whatever. So they have this number. And that's what energy is for them in mathematics. But then when they bring them into physics, they want to bring the word energy. And you say, well, what is energy for the purposes of physics? They say, well, it's this cloud, this smoke. No, what they're talking about is a number. That's what they're bringing it as a thing. So they're saying, I'm going to transfer some energy to you. I'm going to transfer a number to you, followed by a unit. I'll send a unit later. Okay, so this is the problem. They're bringing these words as physical things. And so here, again, it's a question of definitions for the word distance. Length contraction. Are they contracting length? What are they contracting? Well, let's find out. Length contraction, issue of definition. What in mathematics, right? Length is equal to distance and is equal to distance traveled. They make no differences between these three notions. Okay. The problem is the first two, length and distance, are qualitative concepts. They have nothing to do with math at all. What mathematicians are talking about is distance traveled, which is totally different than length or distance. Distance lies between lengths. That's what I like to say. Distance is to space what length is to objects, to things. You can talk about the length of a thing and the spacing between two things. That's the distance between them. Okay, we're done. That's how simple it was. Qualitative all along. We don't know how much, how many, we don't care. We just say, look, the length of this object is from one side of the object to the other side of the object. That's the length of this object. It's a qualitative notion totally. We don't care how much. We don't extend the measuring tape or anything like that. Okay, but what do? They, mathematicians, they measure the distance traveled. And they do it usually with a clock or with a tip of measuring tape. They also count tiles. You know, they make a standard, the meter, the foot, the yard, whatever. And then they count how many of these, right? They put between one wall and the other. They say, the length or the distance between this wall and that wall is 10 meters. What do? Well, they just put 10 tiles, 10, meter tiles, from one wall to the other. And they say, it's 10 meters. So again, what they're doing is counting tiles. And they always count, or they measure, with a clock, with a stopwatch, right? That's how they do it. And that's got nothing to do with the length or distance of physics. And they confuse the two because they say, well, I got to measure the distance. No, we don't. That's only in math. That's when they created units. Human units, the Klingons have other units. But our units here are, pound, kilograms, yard, feet, meter. Those are the units. Time, you can have seconds and, minutes and years and months. They have other units on another side of the universe, right? Okay, so here's the Wikipedia definition. You can see here where they got confused because they don't make any distinction between distance and length. Distance is a numerical measurement of how far apart objects are. No, absolutely not. Distance is separation between objects. And in physics, distance may be referred to a physical what? Length. Yeah, that's not true. Distance and length are two different concepts. In Euclidean distance between 2 points, the Euclidean distance between 2 points is the length of the line segment. No, absolutely not. Distance and length have nothing to do with each other. That's only when you're measuring. If you're measuring, then you're talking about distance traveled, and you're not talking about neither length or distance. Okay, so these definitions are wrong from the start. And those are the definitions they're going to use. And therefore, don't be surprised if they reach irrational conclusions, as they always have, Okay, so here we have the universal moving, and it shows you what they really mean by measuring, right? And here you have it. You're going to measure a table, right? And you don't measure it in a single frame. Okay, what you're doing is unrolling the tip of the measuring tape. You're unrolling it, and so the distance or the length of mathematics, which is known really as distance traveled, it takes up several frames of the movie. You can't do it in one frame. You have to unroll the tip of the measuring tape, and what you're doing there is counting tiles, or simply, counting, assuming just how much each unit is. You can do it also with the clock and say, well, it took 5 seconds, so that's 5 meters. It could be a meter per second. And so there's different ways of measuring, but what they're doing is they're running a movie when they're talking about distance, meaning or length, meaning really distance traveled. It's distance traveled by the tip of the measuring tape. So the distance of so-called distance, right, of special relativity is a movie. Okay, it's not a static distance like in physics, and that's a big problem because people wonder how these words get confused when these people say, "Oh, there was a length contraction, meaning distance contraction," and people say, "Well, hold it. What do you mean? Did the distance contract?" And they're saying, "No, we measure." And this guy measures one thing, the other guy measures another thing, and so we measured the distance differently. Okay, so they're talking about something else, and people say, well, how can the distance increase or decrease? How can the length increase or decrease? No, they're talking about something else. They're not talking about the static distance or the static length. That's where the problem comes in. And unless you grasp that, you're going to be confused always by special relativity. You're going to have to do a lot of thinking to try to figure out what these people are saying. Okay, so here we have a ruler, right? And the question is, did the distance or the length of the ruler contract, or did the ruler contract? These are two different things, okay? The ruler has length, right? But the ruler has a certain length, right, from side to side. Is the ruler shrinking? Or are we talking about a value, something we measured called length, that is getting smaller? Which of the two is correct? And again, this is not a trivial semantic argument. This destroys the theory because you either talk about the ruler contraction or about length contraction. Can't be both. Okay? So which one is it? And what they're saying is, look, it's not ruler contraction. And if it's not ruler contraction, what does measuring differently by different observers, what does that have to do with physics, with science? This is where the problem is. What are we talking about? Are we talking about the ruler getting shrinking, or are we talking about its length, how you measure the ruler, how many tiles, how many minutes or seconds, or how much you unroll the measuring tape, right, the tip of the measuring tape? Which one is it? Or what are we talking about? Has the table shrunk? Is that the issue? Okay, here we have one famous person lately. Her name is Sabine Hassenfelder, and she's going to tell us a little bit about this length contraction. Let's see what she has to say. Have they proved it? Is this a done deal? Here it is.
Imagine you have a photon, a single quantum of light with some wavelength. The wavelength is proportional to the inverse of the energy. What's the energy of the photon? The question doesn't have an answer. The energy of the photon depends on how you observe it. Suppose you observe the photon at, say, color green. An observer moving towards it will see the color shifted to the blue, so at a higher energy, and an observer moving away from it will see it shifted to the red, so at lower energy. What's the real energy of the photon? There's no answer to that. All these energies are equally real. The reason this happens is that in Einstein's theory, the motion of the observer changes what it means for something to be large or small, or to have a high or low energy. And the lengths are not physical, they have no length. They just quantify relations between the points. And since they have no length, there's no problem with them becoming shorter or longer for different observers. It's actually a clever idea.
Okay, so you can see what all this is about. They're saying the motion of the observer changes the length of the thing. Are they talking about the real, actual length of the thing? Well, hopefully not, because otherwise we're all crazy. We're saying that things shrink and expand simply because someone's traveling at the speed of light out there somewhere in the universe. And hopefully that's not the case. No, what they're talking about is how something is measured, and that's got nothing to do with the reality. Number of atoms don't change in an object spontaneously. They don't increase in mass, and they don't get shrunk in size, in length, or distance traveled, simply because someone travels at the speed of light or whatever. That's where the nonsense comes in. That's why people, when they hear this for the first time from special relativists, they say, what are you saying? Are you saying this, and that? And they say, oh, we proved it. Oh, okay, if you proved it, we're done. It's a done deal, right? Yeah, so what they're talking about is measurement. They're not talking about reality, what really happens to the object, okay? And again, all that's got to be done out there. You can't do speed of light or anything close to the speed of light here on Earth. It's got to be cosmic, okay? And if it's cosmic, it's gravity. And if it's gravity, it contradicts special relativity, which says that there is no gravity in special relativity. It's flatland, right? You can't fall down in flatland. Okay, so what is the issue? The issue is that there is no definition, okay? And it's, the contraction is not real. Here we have a fellow who actually contradicts good old Hassenfelder, and you got to listen to him because he says, look, the real trouble here is there's no definition of what length is. Listen to him. As he's from the outside the country, so he's got a little accent there, but I think you'll understand him. Here it goes.
You take the distance of one end of the object and subtract the distance of the other end, and the absolute value of this difference is the length of the object. If it's moving and you take the position of one end and then the other, you have to specify the time at which you measure the two positions. This definition though is only good if you have an absolute simultaneity. But this is where our definition breaks when we jump into special relativity, because in special relativity there is no such thing as absolute simultaneity. The problem of length contraction is not that solid objects shrink just because someone is moving, but it is because the quantity called the length is no longer well-defined quantity in special relativity.
So, do they have a definition for this thing called length? No, they don't. They don't because they're going to make it variable. They're going to say it depends on the motion of the observer. So nothing has length in the universe. Why? Because, if I'm the observer and there's stuff going at close to the speed of light up there somewhere, maybe, right? I'm going to measure something different. But is that measurement correct? Does it match what that thing has in its proper location, its proper, what they call proper frame of reference or whatever? No. Whatever you measure there, if you were there, right, would be different than what you measure from far away, especially if you're moving. And so, what have we learned? What is this nonsense? What's that got to do with physics? What is? And I gave the example the other day. I'll put this up again because I think it's a good example. It's the muon. The muon is supposedly a particle that decays from a pion to a muon to an electron. Then I guess it goes somewhere into an atom, maybe. They say that the muon decays very fast, right? I think it's 2.2 microseconds, and also that's the only thing that they can kind of measure, they say. And so the question is whether The muon senses that. And they say, well, in its frame of reference, it doesn't. Nothing changes. It changes for us, which are observing this thing coming to us. And they say, well, what you have to introduce here is this factor known as time dilation, length contraction and whatever. And here's more or less what I said the other day. I'll just synthesize it in one graph, and that's we have a muon going from one mountain to another. No different really than the other scenario because we're looking at what's happening to the muon and to distance and to length. That's what we're interested in here. And so this muon has distance traveled from the first mountain, mountain A, to somewhere in between them, right? And so the question now is, does the distance traveled, the length between the muon and Mount B change? Okay, because it's traveling at near the speed of light. Or at the same speed of light, really doesn't matter, right? And so the question, does that distance change? And so the first question is that the distance between the two mountains change, okay, because the muon is traveling between them. And so the answer is no, then what are we talking about? What are we measuring? What is this measurement? Has the atmosphere between the muon and Mount B changed? And they say, well, the distance has changed. Well, yeah, so does the distance between one edge of the atmosphere to the other edge of the atmosphere, does that shrink? And so this is where we have problems because people are understanding that, and these people are saying, no, it's the distance traveled that we're talking about. They're not talking about distance or length or separation. They're talking about distance traveled. They're talking about meters and seconds, but they tell it to you like, the distance shrank or the length shrank. And people say, well, what do you mean my ruler shrank? Because the guy was traveling at the speed of light. It makes no sense. And that's where people, get confused. And again, it shows that the language is deliberately misleading. And people don't know what to think out there. And they say, well, if they proved it, I have to believe it because it's Einstein and blah, blah, blah. And that's all we have today, But none of this has anything to do with physics. It's just measurements that they made out there. And it's got nothing to do with the reality of what the object is. And people don't always grasp that. Okay, so here we have a rocket. And it's going to go between two stars. Okay, here it is. Give me a second here. So it's going to fly close to the speed of light, and we have this observer, okay? And he's going to observe this traveling at almost the speed of light, okay? So what do they say for special relativity? That there's a contraction going on. And you can see it here, okay? The contraction of the distance between the stars. Is that what happens? The stars come together because a rocket travels between them at greater speeds? Is that what the observer is measuring? The fact that the distance between the stars, not forget about the rocket, is the distance between the stars coming shorter? In other words, is it decreasing? And so this is what a lot of people understand. They say, what do you mean the distance contracted? What do you mean the length contracted? And they don't really understand that. But what happens when you put them both together? And here, let me show you that. Okay, here it goes. And now you see that not only is the rocket becoming bigger because, mass increases with the speed of light, but the distance is also becoming shorter between the two stars. The two stars are coming together while the rocket is getting bigger. Is that what these people propose in special relativity? I mean, this is total nonsense. And it's nonsense because they're not talking about, the distance between the two stars, the separation between the stars, or the number of atoms that comprise the rocket. What they're talking about is what the observer there, what he's measuring. That's the whole thing. So this is a cosmetic thing, this measurement thing. It just says this guy measured this and this other guy measured that. They measure different things. So who cares? What does that matter? What does that have to do with reality, with what really goes on in the universe? It has to do with people understanding, from their measures what's happening out there. They say, well, what you saw is a mirage. It wasn't really the same size all along. It became more massive and it flattened out. yeah, okay, that's a question of, conscience, of what you perceive. It has nothing to do with what's actually going on out there. And so what can we say about all of mathematical physics? Well, here we have good old Miss Hassenfelder. She's going to tell us what the status is of all this nonsense from mathematical physics after 100 years. These are her words, not mine, okay? So listen to her. Here it is. Listen carefully.
You've been asking me for several years to talk about Stephen Wolfram's theory of everything. I haven't done that, I don't understand what he's doing. But recently I've realized that I don't know what I'm doing either. Indeed, when I look at my news feed, I don't think that anyone knows what they're doing.
Okay, so none of these people know what they're doing after 100 years of special relativity, 100 years of general relativity, 100 years of quantum mechanics, 100 and about 50 years of half of that time for string theory. No one knows what they're doing. That's what she says. She's got a PhD in physics, I think. So she represents the establishment to some degree. She's interviewed. She has her channel, and so she's telling everybody, all these people, all my colleagues, they have no idea what they're doing. That's the status after 100 years. Now, if people say, well, look, all this, she's from the old days, she's stuck in time traveled maybe, right? She's stuck in the old days where they did quantum mechanics and general relativity. We're beyond all that nonsense. That we read that stuff today in our sophomore or even in the freshman years. Today we're into something else. We're into string theory, okay? And string theory is what's going to, unite general relativity with quantum mechanics, and we're going to finally a grand unified theory or theory of everything and blah, blah, blah. And is that true? Well, let's find out. Here we have another fellow. His name is Eduardo. Eddie Witten. And what does Eddie tell us? Well, tells us what the status of string theory is. So just so you know, okay? So listen to him about string theory.
String theory is certainly not a well-established theory. It's a long-term speculative enterprise. We only understand aspects of it. Even after decades of work.
Okay, so after decades of work, string theory is just more poppycock. That's all it is. More equations regarding unicorns and unicorns and leprechauns. That's all it is. They're developing equations. Their work is worthless. All the equations they're developing today are absolute nonsense, poppycock. They're all done on things that don't exist, like black holes, dark matter, dark energy, strings, particles that don't exist, virtual particles, all this stuff. They're developing equations that are totally worthless. We have no use for these equations because all these equations have to do with stuff that does not exist. And unfortunately, the people who are in charge of so-called physics, of mathematical physics, of science, are all these bozos who do a lot of equations on inexistent stuff. And we still cannot say, what causes this thing to fall to the floor. Nobody knows what gravity is, how gravity works. Everybody just knows the equations. And so that's the status of physics today, state-of-the-art physics today, with all these people saying, oh, we have no idea what we're doing. And that's what you're paying for. Okay, I'll be seeing you next week, but I'm going to be on the road. And so just so you know, I may have a little trouble with transmission. I hope I don't. Okay, I'm praying to my God, the devil down there. And so hopefully that I can have a good transmission. But anyways, be aware that I'll be traveling. And so I'm going to continue. I've got some stuff to present, but then I hope the technology helps me.